Have you ever stopped to think about how a digital device, something that only really understands on or off, can do something so smooth, like dimming a light or making a robot arm move gracefully? It seems like it shouldn't be possible, right? Well, it's not magic. It's just a really, really clever trick. So let's pull back the curtain and see exactly how it's done. Here's the game plan. We'll start with the central problem, this digital paradox. Then we'll reveal the solution, this fast switch trick, and learn its secret language, the duty cycle. We'll see how those signals translate into real power, look at how the code works, and then wrap up with why this one concept is just so important in the world of electronics. All right, let's dive right in with the big paradox. In the digital universe, everything is black and white. It's either fully on or fully off. There's just no gray area. And that leads us to the big question, right? If your controller can only shout "go" at full speed or "stop" completely, how in the world do you tell it to go at, say, half speed, or to just speed up a little? It feels like it just can't be done. This really breaks down the problem. A digital signal is like a light switch. It's on, giving it all the juice, or it's off, giving it nothing. But what we want is an analog signal, which is more like a dimmer switch, where you can get all those nice levels in between. So how do we make that basic light switch act like a fancy dimmer? Well, this brings us to the solution, and it's absolutely brilliant. The secret isn't about somehow creating less power. It's about being incredibly smart with time. The technique is called pulse width modulation, or just PWM for short. And the most important word on this slide is faking. PWM is all about creating an illusion. It uses a purely digital on-off signal to pretend it's a smooth, variable analog signal. It is the ultimate digital sleight of hand. Okay, think about it like this. You can't make a light bulb half bright with a regular switch. But what if you could flick that switch on and off, like thousands of times every single second? If you left it on for half the time and off for the other half, your eyes wouldn't even see the flicker. They just average it all out and see a bulb that's perfectly dimmed to 50% brightness. That is the core idea of PWM. So this idea of super fast switching is great, but how do we control it? Well, that brings us to the language of PWM, and it's called the duty cycle. The duty cycle is simply the percentage of time that the signal is in the on state during one of those super fast cycles. And in the Arduino world, we have a really easy way to control this. We just give it a number between 0 and 255. Why that range? It's just a standard 8-bit value. So 0 means 0% on time, and 255 means it's on 100% of the time. Let's look at this in action. If we tell the Arduino to write a value of 0, that's a 0% duty cycle. The signal is just flat, off, nothing's happening. Easy enough. Now, if we bump that number up to 64, which is about a quarter of 255, we get a 25% duty cycle. You can see the signal is now on for just a quarter of each little time slice. If we go to 127, we're almost exactly at the halfway point, 50%. The signal is on for half the time, and it's off for half the time. For a motor, that's roughly half speed. And you guessed it, if we crank it all the way up to 255, that's a 100% duty cycle. The pulsing effectively stops, and the signal is just a solid on, delivering maximum power. So we have this electrical signal pulsing away, but how does a hunk of metal, a motor, turn that into smooth, variable motion? This is where the electronics meets the real world, where physics takes over. This is the really crucial part. The Arduino sends out its PWM pulses. Those go to a motor driver, which is basically a heavy-duty electronic switch. Now, the driver isn't sending half the voltage, it's sending the full voltage, just in those tiny, timed bursts. But a motor has mass, it has inertia. It can't just start and stop thousands of times a second. So its own physical nature smooths out all those rapid kicks of power into one nice, steady average speed. Okay, so let's get practical. When you actually go to wire this stuff up, there are 3 rules you've got to remember. First, on an Arduino board, you can only get PWM signals from the pins that have that little squiggly line next to them, the tilde. Second, those special pins connect to your motor driver's enable pins. That's how you tell the driver what speed to go. And third, and this is a big one, motors need a certain amount of kick just to get moving. A really low PWM value might not be enough to overcome friction, so you usually have to start with a value of 80 or higher. And that last point is super critical for safety.
If you send too little power, you might hear the motor kind of hum or whine, but it won't actually turn. This is called stalling. It's trying to move, but it can't. And all that electrical energy that's being pumped in has nowhere to go, so it turns into heat. And that heat can seriously damage both your motor and your driver board.
Let's see how this looks in some actual code. Probably the best way to really see PWM do its thing is to use it to make a motor speed up smoothly, what we call ramping up.
The code for this is actually pretty simple. We use a for loop, which is really just a way to make the computer count for us. We tell it, hey, start at our minimum speed, say 80, and then just count up really fast to 255. And for every single number in that count, we use analog write to send that new speed to the motor. The result is a beautifully smooth acceleration from slow to full speed.
And how do you think we slow down? You got it. It's the exact same idea, just backwards. We use another for loop that starts at the max speed, 255, and counts down step by step all the way back to our minimum. This is the secret sauce behind all the precise, controlled movements you see in good robotics. Okay, so we've looked at the problem, we've decoded the trick, we've seen the physics, and even the code. Let's just wrap this all up by talking about why this one idea is so fundamental. So let's nail down the key takeaways. First, PWM is how we fake a smooth analog result using a simple on-off digital signal. Second, the duty cycle, that 0 to 255 number, is our control knob. Third, it's a physical property, like a motor's inertia, that does the magic of smoothing everything out. And finally, this isn't just for motors. PWM is an absolutely fundamental concept you'll find everywhere in modern electronics, from controlling LEDs to generating audio.
Look, once you really understand PWM, you've unlocked a whole new level of control. You can move beyond just on and off and start creating things with nuance, with grace, with precision. So now that you know the secret, what are you going to build?